Okay, so I'm very happy to introduce Alfonso Garmendia, who is a postdoc at the Catalan Research Center of Mathematics. Alfonso's research touches on a number of different areas of mathematics and mathematical physics, including Poisson geometry, D-theory, singular foliations, groupoids, and quantization. Borrowing from his own words, he often likes to work on not necessarily new things, but new ways to think about already known things, with the hope of making them clearer. And today he will tell us about a frame principal bundle groupoid of a vector bundle groupoid.
Thank you very much for the introduction. Yes, my title sounds very long, and it may sound complicated, but I mean, in parts, I will try to make it as simple as possible. And first of all, I want to give is the motivation, and the motivation comes from one-to-one correspondence that happens when groupoids are not there. When this is not here, and I should use white. And I will start with motivating principal bundles and motivating, first of all, manifolds. So the outline of the talks, although maybe you have heard manifold before, I will try to give an idea of what a manifold is, the tangent bundle. Then I want to introduce frames, then the frame bundle, and some physical motivation for the frame bundles. And then I will go with the part of groupoids, the tangent groupoids, and the frames of the groupoids, if we have this enough time, which apparently we will have. So I will start with manifolds, and a manifold in mathematics is a weird space that I am drawing here, such that for every point in the space, we can have a chart that make it look like an open set of Rn. So maybe it's a very complicated space, which we don't know, but we get a point, we get something near the point, and that will look like a Rn. And Rn, we can do many things in it. And the most important thing is that we can differentiate and make differential equations. And that's like the main thing of smooth manifolds, that we can have differential equations on them. And something very important for manifolds is also the tangent space at a point P, which we think of it as all the possible velocities that we can have in P. So we have our weird manifold, we have the point, then locally looks like Rn, and then we have in that thing that locally looks like Rn, all the possible velocities that we can have. And that is, of course, isomorphic to Rn, to the vector space Rn, because in the point we have that the space we are living in looks like Rn. And the vector bundle is the collection of all the tangent spaces for every point. So it would be like a pair of elements, a point and a vector, where the point is inside our space, and v is a velocity on that point. So we have a point and a velocity. And that will be a manifold of dimension 2n. 2n because in here we have near P will look like Rn, and the possible values of this one will be also diffeomorphic to Rn. And I'm not sure if at this point there are questions, but if someone wants to hear a little bit more about this, you can ask. When there appears a red dot here, is that I am going to erase everything. So should I continue? I cannot see your faces, but I guess...
you can continue.
Yes, please, yeah.
So I erased everything from the blackboard, and now I'm going to something that maybe some people may not be familiar with, and it's not extremely difficult. Is frames of a vector space. So now we take a vector space. Here on the top, there is a little bit of a summary. And the vector spaces that we want to think of is the velocities as a point P. But this works for every vector space. So we have a vector space V of dimension n, and the frames of them are isomorphism from Rn to V. And in linear algebra, when we see linear algebra, we usually don't use these kind of terms, but we use these kind of terms. We use the order basis, and when we are talking linear algebra, bases are something that is everywhere, and we use bases. So you can think of frames as the same thing as order basis for the vector space V. And this one-to-one correspondence is as follows. If we have E1 to En, an order basis, I say order because E1 to En is a basis, and there is an order. There is the first element, the second, and so on. And that will give us a vector, an isomorphism from Rn to V, which is, here I have an element of Rn, x1 to xn, and I am sending to x1 times E1 plus x2 times E2, and so on, the linear combinations of the x with the e's. That is a function, and there is a function between Rn and V, a map between Rn and V, and it's a linear map, and it's an isomorphism. And vice versa, if we have an isomorphism, then we have an order basis where the first element is phi of 1, 0, 0, 0, 0. The second element is phi of 0, 1, 0, 0, 0, and so on. So these two things are exactly the same. And if I have an element here, I go to this side, and then I have the isomorphism, then I go back, I will have exactly the same element that I started with, and vice versa. So this is a one-to-one correspondence that is also cyclic. And so whenever I say frame, if you are not comfortable with the word, think of order basis, and it's exactly the same thing. And now something interesting is that the frames of a vector space that is also denoted like this, FR of V, is a manifold of dimension n square. And the way that we can see it is, well, I'm not sure if you're familiar with this notation, but in Lie theory, there is GLN, which are all the matrices, n times n matrices, that are invertible. And invertible means that the determinant is non-zero. And having this set here, this is a set, an open set of all the n times n matrices, which is isomorphic to Rn square canonically. And why I know that it is open, because it's when the determinant is not zero, and the determinant is a continuous function, and I am just, I mean, all the elements in R that are not zero is open. So this is the pre-image of an open set from a continuous function. So this is open. It's an open set of R2 of Rn square. And something interesting is, okay, this is a manifold. And then if I have one frame, then I will have a chart for this frame that will give us all the other frames. All the other frames will be written like this. So in the end, this is the structure, a manifold structure there, and that will make the frames of V isomorphic to Rn square. Again, the red dot appears. So if there is some questions about this, you can ask. If not,
you can continue. Please.
What?
You can continue.
Okay. So now to introduce the frame bundle, it is the frame bundle of a manifold of dimension n is, and I will denote it by Pm, is usually denoted by P, or also frames of Tm, are the pairs of elements, a point and a frame on that point, a frame of the tangent space on the point. And this is a manifold of dimension n plus n squared. And why is it that? Well, because the for P, we have a configuration of Rn, and for phi, we have a configuration of n squared. So this will look, this frame bundle will look like Rn plus n squared. And I want to give a little bit of motivation of this, and maybe many people are familiar already with this motivation. But in field theory, a force is seen as a linear map from the tangent of the frames to GLN. And then the equation of motion is written in this way that then I want to explain a little bit why. Here we have, this is any map that will go from the manifold or from an open subset of the manifold to the, oh, sorry. It doesn't matter if it goes from U to PM, because in the end, this equation will not depend on this choice too much. It will go from here to here. And for every point, it will give me a frame. And I choose one. It doesn't matter which one I choose. And after I choose one of them, I have that phi p will go from Rn to TPM. And it's an isomorphism, so I can invert it. So phi p minus 1 will go from TPM to Rn. So what I have here is an element in Rn that is changing over time, because gamma is this is the incognita, which will go from minus epsilon to the manifold. And I can derivate it, derivate this gamma. When I derivate, I go, it is an element in the tangent space for every point, and then I can invert it, and then here I have an element in Rn, which change over the same minus epsilon, and I can derivate again. So in this case, I have something like the acceleration. This is a matrix. And this is like the first derivative. And that this will not only describe the equations of motion in some physical aspects, which I am not familiar with, but it also describes geodesics in differential geometry, which tells you which is the path of the shortest path between 2 points. And when this thing comes as the Levi-Civita connection, but there are many other connections, and for us, this A is not a force, but a connection. And I'm not sure if you want to ask something, because in this part, I am hiding many things. In the other ones too, but in the other ones was easier to know.
Sorry, what's see above M there? Is that U? See on you've phi that takes M to P sub M.
In this part?
No, sorry, in the bit to the left. What's above M there?
C.
I think it's the open set subset of it.
This U.
Yeah.
Yes, I am saying that this U, what I mean is that you don't need a map that goes from the manifold to P, but a local map. It could be a U, sorry. a U, and a U is an open in the manifold.
Oh, I see. Yeah. Okay. Thank you.
So it's not because having a map from the whole M may not exist, and it's not what we need. What we need is just a way to write. I mean, if we are able to write this equation for some phi, and that is that will give us an equation for gamma, and the gamma will not depend on the equation. The gamma, other things will depend on the equation, but the gamma will not depend. So I'm going to continue, and this was more or less the motivation, and what I want to do is there is something interesting here because you have the tangent bundle, and then you have the frame bundles, the frame of the M. In this case, if we can do it in a more general way and have vector bundles, which is for every point in the manifold, there is a vector space. That is something called vector bundles. And then we can get also the frames for any vector bundles. And in a more general case, what we have on this side are principal bundles. And what a principal bundle is that for every point, I have something that looks like a Lie group. In our case, this sign looks like GLN. And now my pen is not working very well. This size will be GLN. And we can change to be GLN for any other Lie group. And the thing is that we can go back. So there will be a correspondence between vector bundles and principal bundles, and from principal bundles to vector bundles. And this correspondence, I want to do it in a more general case. There is this for manifolds, and the one that is more interesting and has more interesting application is the one for the tangent and the frame of the tangent. But in principle, you can do it for every vector bundle and from any principal bundle. And the generalization that I want to do it is to exchange a manifold to a groupoid. And now I'm going to say what a groupoid is. A Lie groupoid. So what I want to do is to exchange M from being M to something that is a groupoid. And I am going to motivate a little bit why. So a groupoid are a pair of two manifolds. I have G and M, where there are a smooth submersion map from G to M to the source and the target. And here we see an element, and I wrote it back. Here is G. Is seen as an arrow that goes from the source to the target, or a symmetry that go from the source, that these two make these 2 points that are in M symmetric or related. And there is a notion of composition, identity, and inverse of arrows. This is that if I have an arrow that ends here in T of G, and another arrow that starts in the same element, I can compose it and have another arrow that starts where this one starts and ends where this one ends. And that will also be a third arrow in G. That will be the composition. Then we have an identity that if I have an arrow, I will have one special arrow here that start and end on the same point. And when I compose them, it gives me exactly the same as the one that I started with, but I will have another arrow for the element in which I start. So each point on M will have a different identity or a different unit. And an inverse is that for an arrow here, I will have another arrow going in the opposite direction, that if I compose this one with this one, it will give me the identity that was in this element. And if I compose in the opposite direction, then it will give me the identity for this point. And if you have some questions right now, you can ask, because this is maybe an object that is difficult to understand. But I see them as a manifold with symmetries. And in the end, the manifold with symmetries will give me a way to see the quotient space. The quotient space may not be a manifold, but then I have two manifolds that model the quotient space. I will continue if there is no more questions. So I'm going to continue with an example that maybe helps a little bit. If I have a manifold M and a smooth submersion that I call Q from M to Y, I can have as the arrows the pairs of elements in M, such that the first map Q of X is equal to Q of Y. This is the source will be the projection onto the first component, the target, and the second component. If I have X, no. If I have X, Y, now I have to compose this one with something that ends where the first one starts. So YZ is equal to XZ. The identity for an element here will be XX, and the identity here is ZZ. And the inverse of XY is just YX. And with this, I have a groupoid structure. In this example is a little bit easy, because in this example, I have M, I have the arrows, but the quotient space is well defined and the quotient space is Y. But we can have some things that are not well defined in the quotient. But it gives a nice way of seeing the elements is M and some equivalence relations. And in this case, the M quotient by the equivalence relation is Y, but
sorry, can I ask a question?
yes.
You say that XX and ZZ are identity elements, so are they equal?
No, that's what I mean, that in a groupoid, every point on M will have a different identity.
Okay, great, thank you.
It is, if you are familiar with categories, this is a category. And then the identity, I mean, is the identity on an object. If you are not familiar with categories, then it's something different. this I will call it the identity in X, and this is the identity in Z. So they don't have to be equal. For the reason why it's called groupoids is because it has something to do with groups, and for every groupoid, I usually write it like this because it's the manifold G, the manifold M, and the source and target arrows is a groupoid and X is in M, then we can have GXX, which are the arrows in G that start and end in X. And this is a group, it's a Lie group. And the identity of the Lie group is precisely the identity that X has. But we will have a Lie group for every point. Every point will have a different Lie group. And every point will have a different identity. Another example that is nice is given a manifold, you can have the path, a manifold M, and G is path in M. Well, if I put it like this, it's not a Lie groupoid, but it's just a groupoid. So this is too big to have a manifold structure. Could be maybe a Fréchet groupoid or something. I'm not really sure. I can also put path up to homotopy, and then that will be a Lie groupoid. That makes it small. And the idea is that I have a path, and I have where the path starts and when the path ends. And if a path starts and ends, if one path starts when another path ends, then I can compose both paths. There is also an example of a groupoid, and then what I am given here will be the fundamental groups of a point, of each point. I'm not sure if that clarifies more or less how groupoids work. I'm going to erase what I just wrote because it was not on the original part. If there is more question, feel free to ask. I'm going to continue. So something that we can do is that, okay, this thing is a manifold and this thing is a manifold. So we can create the tangent of that manifold and the tangent of this manifold. And these maps that we have here are a smooth map. So we can differentiate and create maps on the tangents. So I have here the source, the target. So here I have the differential of the source and the differential of the target. We will have identity map that for every point in M will give us an identity element in G. And we can also create the differentiation of this map to have a map here. And in the end, what we have on this side is a groupoid. And that is what we call a vector bundle groupoid or a VB-groupoid. Why? Because on this side we have a vector bundle, on this side we have a vector bundle, and on the vertical lines are groupoid morphisms. And groupoid morphisms are, this is a, the vertical lines are vector bundle morphisms, and the horizontal lines are vector bundle, are groupoid morphisms. This is a bit confusing. This is groupoid morphism, which I was not planning to talk about. And these ones are vector bundle morphism. So here is a vector bundle, here is a vector bundle, and I am passing from a vector bundle to another vector bundle. This one, this one here is a groupoid, and this one here is a groupoid, and I'm passing from a groupoid to another groupoid. And the basic example of a VB groupoid is exactly the tangent. And it works is just because we can differentiate all the maps that we have on this side. And it's also an extremely interesting object. There are many constructions that you do with groupoids that then in this tangent groupoid becomes extremely natural. If let's see if no, okay. If the idea to look on this side was because we wanted to see the quotient space of this element, of this groupoid, and that quotient was weird, then this side will give us the tangent of the quotient space. That is more or less the philosophy. And what I am trying to do with my collaborator, that is Francesco Cataffi, is to get the correspondence between vector bundles and principal bundles, but in the groupoid level. And naively, one can expect that then if we have here, this one is a vector bundle, and this one is a vector bundle. So we can have the frames of TG and the frames of TM. And maybe expect that this one is also a groupoid, but it is not. There is not enough information like to go from the bottom to the top. Many things are not natural here, so this one will not work. And instead, we choose some special frames on TG. And on the base, we take something that is frames of TM times frames of something that is called the core of the VB-groupoid, and in this case is the kernel of the S restricted to M. This is C. And with this information, we can create a new groupoid, which is made out of the frames. And then is this one also a Lie groupoid? I mean, is this one also a manifold, and is this one also a manifold? And that's what I am going to give a little bit here. So this now this is the part in which I am going to kind of improvise. I have And now becomes more abstract. Sorry. So in this side, I have a group point, and in this side I have vector bundles on the arrows of the group point and a vector bundle on the base of the group point. And I want it to be a VB-groupoid, so a vector bundle groupoid. So this one here is also a groupoid. In the case we had before, this side here was the tangent of G, and this one here was the tangent of M. Now we get the frames and the special frames of EG are. So also the diffeomorphisms now, let's say that this one here is of rank K. So the dimension for every point, the dimension of the vector space is K. And in this one here, we say that the rank is L plus K. When we have a PB-groupoid, the dimension of this one has to be bigger than the dimension of this one always. And so this is the excess of the dimension. And in here will be diffeomorphisms from RLK plus K to, and I usually, here I have two things. P and phi, such that P is in M, no, P is in G, and phi goes from RKL to EGP. EGP is the vector space in P. In the case that we had before was TPG in the case of the tangent. Now here what I wrote is any frame, but I have also other conditions to make it special, and is that phi restricted to RL times 0 is a frame in the kernel of S at P. So this will be a subvector space of the thing that I have here. And I ask that the first coordinate give me a frame for that subvector space, as the first coordinate here is a subvector space of this one. And that phi of restricted to 0 times RK is, and then I apply T, is a frame for ETP, EMTP. But this maybe is a lot of conditions. the first condition implies that when here I put an S and here I put an S, I also have the same. I mean, it will also happen that if I have first this will be a map from RK to EG, and then when I apply T, I will go to EMTP. So the thing is going okay. And in here I have a map from RL to EG, but I am restricted to a subspace which will be also of dimension L. So this is also okay. If I restrict to this frame, there are a complicated way to define the target and the source and to something that is frames of the kernel of S restricted to M times the frames of EM. And you kind of see here these two things appearing and why it is what they are appearing in the base and not just the frames of EM. But playing with these two, we could find some source, target, composition of elements here, and so on. And then look, we have two frames here, and there will be a matrix that will change two elements here. We see what are the kind of matrices that change from one element to the other, and this kind of matrices will be something like this A G0B, where this part is in GLL and this part is in GLK. And this becomes a little bit tricky because this one will depend, the values that this one can take will depend on the points in M, basically. But these two will always be something in GLN and something in GLK. But this one can change from point to point. And that will give some groupoid structure over GLL times GLK. And we can also make this parameter there somehow. And we will have another groupoid here where the piece lives. And now I'm getting extremely abstract and I'm not sure if you want to hear more details or you have more questions. But I wanted to kind of motivate what we do and kind of see the ideas without going to the details. But this is the new work I have been doing with Francesco Cataffi and will appear on Archive soon. Which is trying to make the frame bundle of a vector bundle groupoid. We also show that the opposite way, that if we have something that looks like the frame, these kind of frame bundles with this kind of elements that make change from one element to the next, we can then create a vector bundle groupoid. So we have, again, the one-to-one correspondence that I said before. Is there some questions about what I just showed?
I have a question about a little bit further back.
Right.
So I guess in terms of understanding the groupoid with slightly more intuition, all right?
Mm-hmm.
So we have these two nice submersion maps, and we have some G on the manifold, right? And can you just sort of briefly go over the nature of how G is relating to the two maps S, T, like what it's doing to them?
G, you means this G?
No, like the little G, the element inside the groupoid. The arrows.
Ah, the arrows, this little G.
Yeah, because you have the two primary arrows, S and T, these maps from the groupoid into the manifold.
Yes.
Then you have G.
G is an element in, now I here there is also the mistake. G is an element on the groupoid.
Okay.
So in the example that I give that of curves, G is a curve.
Okay.
And in here is a pair. G will be XY. This will be G. So this is just saying that, I mean, the example I'm giving here is a bit dumb, but I have XY, and I am just saying this is an arrow between Y and X. And I'm saying these two are related. And these two, in this example here, these two are related if they map to the same thing in Y. And the philosophy is instead of seeing Y, I can see M and the relation. And M and the relation are smooth. Y sometimes cannot be, I mean, in this case that I'm asking for submersion, Y is smooth. But sometimes Y is not smooth, even though M and the relation that I have is smooth.
Okay. And then yeah, okay, so I see. And you essentially you need the two submersions such that you get a group type structure out of this, right? That's why.
Yes.
Yeah, okay.
The submersion here is basically for the composition.
Yeah.
Because the composition will go from, I have, I can only compose an element here that ends where that ends where the next one starts.
Yeah.
And I want this to be a manifold. And for this to be a manifold, I need either T or S to be a submersion.
Okay.
I need only one of the two.
Okay.
But there is also, I have also the inverse map. And in the inverse map says that if I apply T composed with the inverse map, this will be exactly the same as the source. And that it just is telling me that that if T is a submersion, then S is also a submersion.
Okay, thank you. Yeah, that makes sense.
So the submersion is asked for this to be a manifold, and we ask both because if we ask one, then the next one has to be also. I can also give another example of a groupoid that I kind of like, and it's related to this talk, but it doesn't motivate why I want to have the frames of. I mean, this one motivates why the frames of the tangent of a groupoid is interesting, but the other example that is very, I don't know, I really like it, but it's not going into that direction. Is I will give it anyway. So we have let's say we have Tm. It's using all the many things that I'm given here. Tm, and we have P of m, that is the frames of Tm. Now we can have frames of Tm times frames of Tm. And GLN is acting on this, like if I have a map from Rn to some TPM and a matrix, I can have phi and a matrix A. I can have phi A, which will also be a diffeomorphism from Rn to TPM. So this is an action. And now I can have the diagonal action in here and do a quotient by GLN. Now I have a phi, a frame on the point P and another frame in another point Q. So the elements here will be classes of this kind of pair, and then the source of this kind of element is P and the target is Q. And then I can compose like composing maps. If I see it like this, is maybe not so easy to understand. If I think of them as bases, here I have a basis of the P, here I have a basis of the Q, and I just have the pair composition of bases. Like if I have here a starting in another base, a Q, and I go to phi W, I can compose these two, and this one, I get these two erased, and I just have this one with this one. That will be the composition. I'm not sure if I am making myself understand. I am kind of improvising. But why I am saying that this is interesting, because this is exactly the same as maps from TPM to TQM, being P and Q any other elements there. And why these two are the same? Because this one is exactly the same. An element here is an order basis in TP, and an element here is an order basis in TQ, and there will be only one diffeomorphism that sends this basis to this other basis. And if there is, so I have base 1 in Q and another base in P. There is only one diffeomorphism that goes from here to here. And this diffeomorphism, I can write it in a different basis, but then if I have B prime and BQ prime that give me the same diffeomorphism, it means that I am applying here a matrix, and here I am applying also a matrix. So the action that I'm given here, how to say it, if I have two different classes of this action, it's giving me the same diffeomorphism. And in the end, this pair of element times the quotient is the same as map from TP to TQ. And that will be a groupoid. And it's a smooth. Like this kind of thing is also a manifold. It looks extremely big, but it's not that big as one I think is. Will be a manifold of, I think of dimension also n times n square. No. 2n times n square. Not sure if anything I said here was understandable, but it's kind of my favorite groupoid, and and I could have introduced it a little bit better, but
So this is like a basis independent means of constructing the set of maps between
yes,
tangent spaces. That's why you're quotienting out like GLN, right?
exactly.
Yeah, okay. Makes sense.
Exactly, and that is a groupoid, and it's a
Okay.
Lie groupoid of and a manifold of dimension 2n plus n square. And one can also see the tangent groupoid of that and then taking the frame again, which I'm not sure to where it will lead. Maybe a very interesting object, or I mean, probably it will be probably a very interesting object that has no applications, but and I think maybe cool. The one that probably has applications is when I think of the groupoid as the quotient and not all the arrows. But maybe this one has application too. It's just that I cannot see it.
Whenever you do this like tangent groupoid construction,
Mhm.
you essentially always get a VB groupoid back, right?
Yes.
And if you keep doing it,
Yes.
what happens? It is in some sort of limit.
Well, you can keep doing it.
Yeah.
It just becomes bigger and bigger and bigger. Like I have then I have TG, TM, and now this one is a groupoid, and then I have TG and TM. And this one will also be a groupoid. But I think like everything will be encoded on the first information. Then in here I have a linear part and a non-linear part. And then when I go to the tangent, I guess the linear part of this one is just repeated on the next one.
Oh, okay. That's not too interesting.
And maybe that's why people stopped here, maybe.
Okay, thank you.
You're welcome.
But if I remember correctly, I think groupoids also show up in relation to some of Harer's work on stochastic differential equations. Is that right?
Yes. Well, I'm not sure on stock. I mean, this sounds to me also to groupoids appear on pseudo differential operators, which I know has something to do with stochastic differential equations, but I don't know the relation. And in so the idea of pseudo differential operators, or well, with seeing differential. Well, let's start with something. I have a differential operator that I call D from I think C infinity M to C infinity M. And depending on how regular this one is, one can have the Schwarz kernel of it. And the Schwarz kernel is seen as something that is in the distributions of m times m. And the idea is that this thing here is like a matrix, and then I can write it like if it was going from an infinite dimensional matrix going from an infinite dimensional space to another infinite dimensional space. So d of f may be some kind of integral of the here in x of the sd x y f of y dy. But the groupoids appear is to study special kinds of differential operators, well, of operators, not necessarily have to be differential, of operators. And depending on the class that you choose, you can exchange this m cross m to be a groupoid. Like instead of being m cross m, you can put the m squared that I put before, where m squared was the pairs xy in m squared, such that q of x is equal to q of y, and q was a map from m to y. So that is also a different logic to study groupoids. And when you see it like this, the tangent also appear when you want to compose elements like this. There is something like the wavefront set. And the wavefront set of an element here is something that lives in the tangent or the cotangent. I think it's in the cotangent of the groupoid, or what you have here. I mean, being this G is the distribution of G, the distribution of m times m, or the distribution of m squared, and the wavefront set is something that is in T star G, and that is this T star G is also a VB-groupoid, but it has a more complicated description. So I am that's why I am not explaining it here.
But is there a sense in which this is better equipped to deal with irregular structures?
Yes, like irregularities of the operator or the operators that you are considering.
Yes, for example.
Mm-hmm. This also has something to do with the deformation quantization, but it's like going a little bit in loops. I'm not sure if I should mention.
I'd like to hear that.
Let's see. The operators, when I go to the Schwarz kernels, it go into something like this. But then we can also have the symbols of these operators or of these distributions, and those symbols we can see it as functions on T star M. The interesting thing here is this is symbol map. the symbol, there is not enough information to recover the Schwarz kernel or to recover the operator out of the symbol. So there is a lack of information, but the symbol is one of the properties that the operator has, and the nice thing about it is that if I have D1, D2 minus D2, D1, that is the commutator, and I take the symbol, the first part of the symbol will be a Poisson bracket between the symbol of D1 and the symbol of D2. And this Poisson bracket is something that only appears in T star M. And what I'm showing here is kind of a dequantization. Here I have, or reverse quantization. In physics, you can create the Hamiltonian systems in T star M. And the idea of quantization is to, for every Hamiltonian in the Hamiltonian system here, create an operator that describes the mechanics. And then the idea is that if I go from Hamiltonian to operators and go back using the symbol, I have that it satisfies that the bracket here is the Poisson bracket here. And this is using a lot of groupoid theory. Like if I change here a groupoid, I put here any groupoid, what I will have here is something that is called the dual of the Lie algebroid of the groupoid, and I will have functions here. And this one is also a Poisson manifold, and I mean, it's like these things that work in a very specific case can be generalized for when I put here a groupoid in a kind of canonical sense. And then you have like quantizations, but of weird spaces that may not be useful, but that you can do it. I mean, well, no, not that you can do it, but that you can make sense out of what quantization of these kind of spaces will be and how they can be useful. I think it will take me more time to, or I have to prepare to say this in more detail. Why they are, but I'm not sure if I give well the idea of the relation. Is there more questions? I can also put here the thank you template. And there is, you can see part of the talks except the part that I improvised. And a weird way to say thank you, like theta and q. Thank you.
Thank you.
Maybe we can thank Alfonso.
I should see your faces. Okay, I can see your faces.
Perhaps I can stop the recording, but if there are no other questions.
There is something in the chat.
Just thank you.
Theta and q.